Welcome to The Explainer. You ever stop and think about all those plastic pipes running underground and through our factories, carrying everything from water to critical chemicals? Well, today we're going to take you on a guided tour of the engineering rulebook that makes sure all of that is done safely. We're talking about Chapter 7 of ASME B31.3.
So let's just dive right in with the big question, right? Why do we even need a whole separate rule book for plastics? I mean, can't we just use the same rules we've had for metal pipes forever? Well, turns out that's a definite no-go. It would be a total recipe for disaster.
And the reason why is pretty simple when you think about it. They're just fundamentally different materials. It's kind of like comparing a power lifter to a gymnast. Metals are your power lifters, super strong, great with heat, but they're prone to corrosion. Non-metals, on the other hand, are the gymnasts, incredibly flexible and they won't corrode, but they just can't handle the same strength or temperature demands. So you can't give them the same training manual, right? They need completely different safety playbooks. All right, so here's our game plan for today's tour. First, we're going to talk about why this code for plastics even exists. Then we'll get into the real nuts and bolts, the design conditions and allowable stresses. After that, we'll look at how you actually design the individual parts and joints. And finally, we'll zoom out and see how it all comes together as a whole system.
Okay, Section 1. Let's talk about a code specifically for plastics and really get to the why behind this whole Chapter 7.
So you can think of the main B31.3 code as like the master cookbook for all industrial piping. And Chapter 7, that's the special section in the back for, let's say, alternative ingredients. It's where you find all the must-follow recipes for working with plastics and composites, making sure everything is done safely and performs the way it's supposed to.
Okay, let's move on. Section 2 is all about the foundation of the design, the conditions, the criteria, and the stresses.
And you know, the code is actually structured really intelligently. It basically forces engineers to do their homework before they start building anything. This first part, Part 1, it's all about defining the fundamentals. You have to lay out the operating conditions first before you can even think about doing any calculations.
And it really breaks down into a pretty straightforward three-step process. Step 1, you've got to figure out the design temperature. How hot or cold is this thing going to get? Step 2, define the design pressure. Simple enough. And only after you've nailed down those two things can you move on to Step 3, which is figuring out the allowable stresses the material can handle under those exact conditions.
And this right here, this is what I find so fascinating about the code. It doesn't just give you a formula. It actually says the designer has to be satisfied with the material. That word, satisfied, is huge. It puts all the responsibility right on the engineer's shoulders. It's a great reminder that this isn't just about crunching numbers, it's about professional judgment and expertise.
All right, Section 3. Now that we have our foundation set, let's talk about designing the actual components and joints. You know, the building blocks of the whole system.
Okay, don't panic, we're not going to make you do the math here. But what's so crucial to understand is that the code gives engineers the exact formula to figure out how thick a pipe's wall needs to be. And you have to get this right. I mean, if you make the wall too thin, you're looking at a potential catastrophic failure. This is really where the engineering rubber meets the road.
And this is what's so brilliant about the code. It's not just talking about the straight runs of pipe. It covers literally everything. We're talking bends, elbows, branch connections, flanges, valves, the whole shebang. Every single piece of the puzzle has its own set of rules to make sure the entire system is designed to the same safety standard.
But think about it. You can have the most perfectly designed components, right? But if the way you join them together is weak, the whole system is compromised. The joints, that's almost always the weak spot, the point of highest stress. So it's no surprise the code pays a ton of attention to them.
And yeah, the code gets super specific here. It doesn't matter if you're using glue to bond joints, or bolts for flange joints, or even old-school threaded joints. There is a dedicated section with rules for each method. It's pretty much a masterclass in how to build a leak-proof system no matter how you're putting it together.
Okay, on to our final section. Let's zoom out and look at the big picture, system-wide considerations. We've got our components and our joints. Now, how do we make sure it all works together as one safe system? All right, let's talk about a really big deal for plastics, flexibility. You see, when temperatures swing, plastic pipes can expand and contract way more than steel. And if you don't plan for that movement, well, things can buckle, snap, and fail. So this whole section is critical. It's about designing a system that can, breathe and move without breaking.
So how do you manage all that expansion and contraction? Well, it all comes down to proper support. You can't just lay the pipe down and call it a day. The code acts kind of like a choreographer, right? It tells the engineer exactly where to put supports, where to put guides to allow movement, and where to put anchors to lock things down. It's all about controlling that movement gracefully.
And look at that, we've come full circle, right back to where we started, the materials themselves. The code is incredibly strict here, especially when you're dealing with hazardous stuff. For instance, you can't just run any old plastic pipe above ground if it's carrying something flammable. The safeguards have to be extensive because the stakes are just way too high. The code makes sure engineers are using the right tool for the right job.
So, when you boil it all down, what's the big takeaway from our tour today? It's that the code isn't just a stuffy rulebook. It's really a framework for sound engineering judgment. It's not a substitute for it. It's a critical safety net, for sure, but it's a tool, a powerful one, that helps skilled engineers make the right decisions to build the safe infrastructure we all rely on every single day.
And that really leaves us with one final thought, looking towards the future. I mean, new composites and polymers are being invented all the time. So the big question is, how will this engineering rulebook have to evolve? The challenge is going to be keeping up with that pace of innovation and making sure the rules are there to safely unlock the potential of all these amazing new materials.